Suppose I asked you to find the absolute value of a number. So, for example, if I asked you to find the absolute value of something like 3, we know the absolute value of 3 would just be equal to 3. And if I asked you to find the absolute value of a negative number, something like -2, then we know that the absolute value of -2 is just simply 2. Now, what if I asked you to find something like the absolute value of 3 plus 2i, a complex number? Well, what would this be equal to? And so far, we don't really have a way of answering that. And I think something that will be really essential or is necessary for us to answer this question is to make sure that we have a thorough and full understanding of what absolute value means. And contrary to what a lot of people think, absolute value does not simply mean that we take the number and we make it positive. That's not what absolute value actually is. Absolute value is simply the measurement of that distance from the origin or from 0. So if we're looking at 3 plus 2i and we're trying to find its absolute value, we're really asking ourselves, how far is this complex number from the origin? And if for us to really visualize that, we've got to go back a little bit. And remember that complex numbers can be graphed on what's called the complex plane. This is very similar to the Cartesian plane, but remembering that the complex plane means that our what we think of as our x-axis is really our real axis, and our imaginary axis, or what we think of as our y-axis, if you will, is our imaginary axis. So a number like 3 plus 2i, which would be this number right here, 3 plus 2i, what we're really asking ourselves when we want to find the absolute value of this number is how far is this number from the origin? How far, what is this distance here? And the way we would actually approach this is to think about 3 plus 2i, this complex number, in the same way that we would think about a vector. In other words, we can really just redraw this as looking at this 3 plus 2i as some sort of vector here with a component form of 3 comma 2. And do we know how to find the length of this vector? We absolutely do. It's called our magnitude. So finding the absolute value of a complex number, 3 plus 2i, is the same thing. So let me go back here to our notes. Finding the absolute value of our complex number, 3 plus 2i, is the same thing as finding its magnitude. So we would describe this here, just so we're clear about the notation. Z is any complex number here, any complex number. And finding the absolute value of Z, the absolute value of Z, another word for that is to describe this as the modulus. Finding the absolute value of a complex number is the same thing as finding its distance if we treat it as a vector. So let's actually try this problem. So let's take the number 3 plus 2i. Let's first plot this number. So 3 plus 2i, make sure we know what this looks like. This is our real axis. This is our imaginary axis. 3 plus 2i would be right over here. This would be 3 plus 2i. And if I take a vector to represent 3 plus 2i, it's a vector in component form, 3, 2. So let me just call this vector here. This vector is 3, 2. That's its equivalent vector. If I want to find the absolute value of 3 plus 2i, the absolute value of z, or the absolute value of 3 plus 2i, it's simply taking the magnitude of this vector, which is 3 squared plus 2 squared, so 9 plus 4. This would be equal to root 13. And you can do this with any complex number in any particular quadrant. So you can go ahead and pause this video and try checking your solutions for B through D and check it with the solutions I have uploaded to Google Classroom. So this is a really important step in us understanding something called the polar form, which is another way of describing what we call the trigonometric form of a complex number. And basically the idea here is that we can write any complex number and treat it like a vector. And in the same way that we use trigonometry to describe the angle of a vector, we can then describe or write that complex number in trigonometric form or in terms of its trigonometric values. Now, why on earth would we take something that looks so beautiful, something like a really basic complex number, something like this, 3 plus 2i, and rewrite it in trigonometric form using its angles or trig functions? Well, the answer is because, believe it or not, it's actually a lot more effective to work with the powers and roots of complex numbers, which we'll do in the next lesson. In other words, if I asked you to take 3 plus 2i and raise it to the 7th power, it's much easier to do that when it is in polar or trigonometric form than it is to expand this out and multiply this out 7 times, or to even take the 1/4 power of this to find the 4th root of 3 plus 2i. Working with polar form is a lot less complicated. So we'll do that in the next lesson. But to go back to understanding how to rewrite a complex number in trigonometric form, the key is to really understand that a complex number, z, is simply a plus bi. Well, let's define each one of these things. To write this in polar form, a plus bi, understanding, so this point here, a plus bi here, is understanding that our a represents our horizontal value. This is our horizontal value or horizontal component of our vector. And how have we described horizontal values using trigonometry? We would say a then is equal to whatever our r value is times cosine of theta, right? If we think back to what we said with vectors, it's our magnitude times the cosine of our angle gives us our horizontal component. Well, what about b? B then would be, you guessed it, r times sine of theta. So writing a plus bi, this complex number in trigonometric form, would be the same as writing in, so this is the complex number in standard form. So I'll write this in standard form, not to be confused with standard form for vectors, but standard form for complex numbers. To write it in, and I'll do this in a different color, in polar or trig form, is to say this complex number can be written as r cosine theta plus r sine theta. So this is our a, this is our b, and then times, and I'll just do this in a different color, I. So a plus bi is written this way in polar or trig form. Now, we can actually clean this up a little bit since we're using r twice, and so we can say z is equal to r times cosine theta plus I sine theta. And we just move that I to the front just to make it a little bit easier to work with, since we don't want to get mixed up with the angle there. And there's also what we call an abbreviated form. And this is the one that we'll most commonly use. But there's also an abbreviated form that I'm okay with you using in class. And the way the abbreviated form looks, and I'll just do this in a different color, abbreviated form, abbreviated, is to say z is equal to r, and then we would say cis theta. I know, it seems like almost like a cop-out, but it's a totally valid form, okay? So here we have a complex number that's in standard form, and what we can do is rewrite that complex number in trigonometric or polar form. A couple things we want to just remember here as we look at all this. R represents our magnitude. It's the magnitude of our complex number, or our modulus. Okay, so just want to make sure that we're clear on that. And we would find R by simply doing the absolute value of our complex number, just the same thing that we just discussed earlier, and then also just making sure we understand that it's the magnitude of our complex number here. Okay, so let's go ahead and try a few practice problems where we convert or rewrite a complex number that's in standard form into polar or trigonometric form. So let's take a look at this first example. So we've got -6 plus 6i. So if you look at this, we're going to need two things. Effectively, every single time we convert a number into polar form, we need two things. We need its angle, or its argument, and we need its modulus, or the magnitude, or its distance from 0. So let's start by finding r. Let's find that distance. So we're going to find r. And remember, r is equal to the distance from the origin. It's our magnitude. So in this case, what is our r? Our a value is -6. So we got -6 squared plus our b value, which is 6 squared. So r is equal to 36 plus 36. That gives us 72. And we can actually simplify that further. We can say r is equal to 6 root 2. Okay, next, and let me do this in a different color. Second part is for us to find our angle theta. Let's find theta. So in other words, if we treat this complex number like it's a vector, we're finding its magnitude and its direction angle. So we would say theta is going to be equal to the arctangent of our vertical over our horizontal, or in this case, 6 over negative 6. So the arctangent of -1 would give us negative pi over 4. And you can also say this in degrees, but typically with trig form, we usually work with radians, and it's actually going to make our lives a lot easier when we start doing more operations with trig form. So try to write this in radians. So this is going to give us negative pi over 4. Now, before I kind of firmly plant that as negative pi over 4, it's a good idea for us to make sure we understand where is our complex number. If we graph -6 plus 6i, so we go -6 plus 6i. So remember, this was our real, this is our imaginary. -6 plus 6i is over here in quadrant 2. Okay, this is where our complex number z is. Well, by doing the inverse tangent, we ended up with negative pi over 4 down here. So it's always important for us to think about where our complex number is and ask ourselves, how then can we use negative pi over 4 to express what the actual angle is here? What is this angle theta? Theta would actually be negative pi over 4, this angle, plus pi. That's how we get it into quadrant 2. So theta is actually 3 pi over 4. We don't want to use negative pi over 4. Our angle is actually 3 pi over 4. So now that we have all that, we are ready to write our number, our complex number in trig form. So we know z is equal to r cosine theta plus I sine theta. So z is equal to our r value, 6 root 2, times the cosine of our angle, 3 pi over 4, plus I sine 3 pi over 4. Kind of running out of space there. Oh, we had plenty of space to work with. I don't know why I was writing that so tiny. So there is our number in trig form or polar form. Okay, oops, not sure why I did that. Let's see if we can get a better shot. Nope. There it is. If at first you don't succeed. All right, so we've got trig form here. And if you recall, I'm also okay with you writing this in abbreviated form. So if you had just written 6 root 2 CIS 3 pi over 4, that totally would have been fine as well. Abbreviated form. That is valid. Okay? All right. Now, what if we take a number that is already in standard, or excuse me, that is already in standard form, and, oh, excuse me, in polar form, I apologize, a number that is already in polar form, and we want to rewrite it into standard form. So let's take the same number, let's take 6 root 2 CIS 3 pi over 4, so our trig form, and let's write it back into standard form, just so we know how to do that. So we're going to take 6 root 2 CIS 3 pi over 4, and I'm going to write it out just so we can kind of see exactly what we need to do. So we're going to say cosine of 3 pi over 4 plus I sine 3 pi over 4. And the way to write this into standard form is really just to evaluate it. We're going to write 6 root 2. What is the cosine of 3 pi over 4? Negative root 2 over 2. What is the sine of 3 pi over 4? Positive root 2 over 2. And then we're going to distribute that 6 root 2 by everything. That would have the root 2's become positive 2. So we just have negative 6 plus 6i. So there's our standard form. Standard form. Okay. So the way to get from polar form back into standard form is just to evaluate. Now, the final thing I want to discuss with you all is how we would actually multiply and divide complex numbers in polar form. I mentioned earlier that the reason we even spend time converting a complex number that's in standard form into polar form is because it's much easier to work with powers and roots. And the step to getting there is to make sure we understand how to multiply and divide with complex numbers that are in polar form. So I want to do this first problem by just a little bit of the longer way, and then make sure that you understand the shortcuts so that we don't always have to do every single step I'm about to show here. So if we are multiplying these two complex numbers, z1 and z2, well, the first thing is to understand, well, the first thing we can just do is multiply the two moduluses, which I don't know, do you say moduli? Not sure. Z1 times Z2 is equal to 2 times 3. We're going to have that. We're going to say R1, which we're going to just label this as our R1, and this is our R2. So we're going to say R1 times R2. Okay? Now, this next part here, and let me just change colors. This next part, if I wanted to then multiply these two binomials, because we have two binomials here, and I'm not going to write it all out, but if you were to take cosine 5 pi over 6 plus I sine 5 pi over 6 and multiply by cosine 7 pi over 4 times I sine 7 pi over 4, and to actually, and I know some teachers don't like using this term, FOIL it out, basically multiply and expand that all out, you would actually see that that expanded form is really just the same thing as, and I'm going to let you pause the video and think about it, or maybe even work it out, but it's really just the same thing as the sum formula for cosine and sine. And again, for the sake of time, I'm not going to write that all out, but what we effectively have here is that this is theta sub 1. These angles are theta sub 1. These angles we can call theta sub 2. And so what we'd actually see is this is equivalent to theta sub 1 plus theta sub 2 plus I sine theta sub 1 plus theta sub 2. So the result of multiplying two complex numbers that are in polar form with one another is equivalent to doing R1 times R2. In other words, just multiply the two moduli, and then it's CIS, or the cosine and sine, as written above, of theta 1 plus theta 2. In other words, to put it in very simple terms, multiply the moduli, add the angles. So let's actually try that with this problem that we have here. So z1 times z2 is, we're going to multiply our two moduli, 2 times 3, CIS, and we're going to add the two angles, 5 pi over 6 plus 7 pi over 4. Well, let's see here. We want to make sure we have the same denominators, so we're going to have the 6 CIS, and that would be 24 would be our common denominator. That would be 20 plus, what do we have there? 42. So that's going to give us a number, and we want to make sure that our number is between 0 and 2 pi if we can, but I'm just going to go ahead and, well, actually, no, sorry, we don't want our denominator to be 24. 12 will just work fine. I thought I was getting a little bit too large there. So that's just going to be 10 pi plus 21 pi. That's 31 pi over 12. 31 pi over 12. And there is our product of those two complex numbers. You can also write this as CIS 7 pi over 12 if we want to express our angle between 0 and 2 pi. Well, I'm not going to fully explain the entire process for how we derive the formula for dividing two complex numbers, but it's pretty similar. To do z1 divided by z2, it's the same process, but just with division, meaning we're going to divide our two moduli. So in this case, we're going to go 10 divided by 2, CIS. And again, if you were to expand these all out, what you would see here is what we're actually going to do is we are going to subtract our angles. So we're going to say first angle, pi over 3, minus the second angle, pi over 4. So the quotient of these two complex numbers would be 5 CIS. This would be 4 pi over 12 minus 3 pi over 12, which is just pi over 12. So there is the quotient of these. So hopefully you have a pretty good sense now of how to take a complex number and rewrite it in trigonometric or polar form, and start the process of multiplying and dividing with complex numbers in these forms.